It begins not with a bang, but with a whisper. On a clear, cold night, at an observatory perched high on a Chilean mountain, a young astronomer named Dr. Aris Thorne is finishing his shift. He isn't looking for doomsday. He's mapping the faint, distant movements of Kuiper Belt objects, those icy bodies beyond Neptune. His telescope, a marvel of modern engineering, takes thousands of images of the same patch of blackness. A powerful computer program then compares these images, searching for anything that has moved against the static backdrop of faraway stars. It's a routine task, one he has performed 1,000 times before. Tonight, however, the computer flags something unusual. The program highlights a tiny, almost imperceptible smudge of light. It's faint, and it's moving faster than the other objects in its vicinity. Thorne leans closer to his monitor, his heart beginning a slow, steady drumbeat. He runs a diagnostic, checking for sensor glitches, checking for atmospheric distortions, checking for software errors. Everything comes back clean. The object is real. He pulls up archival data from other sky surveys, his fingers flying across the keyboard. There it is again, a week ago, even fainter. And a month before that, barely a phantom. This isn't some distant ice ball minding its own business. Its trajectory is sharp, its path cutting across the orbital planes of our solar system. The screen flashes a warning, collision probability 99.8%. The date of impact is projected, September 3, 2025. The object, now designated 2024 XF1, is no mere rock. Preliminary estimates suggest it is nearly 10 kilometers wide. A planet killer. He picks up a secure phone, his hand trembling slightly. The quiet discovery in the lonely dark is over. The clock has just started ticking for every single person on Earth. So, how did we even see it coming? How do we find these cosmic bullets in the infinite shooting gallery of space? It isn't magic, it's science. Patience. Some seriously powerful tools. Our planet is guarded by a network of cosmic sentinels. Telescopes on the ground, telescopes in orbit. These aren't the kind of telescopes in your backyard. They are wide-field survey instruments. Pan-STARRS in Hawaii, Catalina Sky Survey in Arizona. Their job? Take massive pictures of the sky, night after night, creating a colossal cosmic flipbook. The real magic happens next, inside powerful computers. Specialized software compares fresh images, pixel by pixel, to pictures of the same sky taken hours or days earlier. Distant stars and galaxies don't move. Fixed background. An asteroid, our neighbor, will have shifted its position. The computer flags this tiny moving speck of light. This is our first clue. Scientists follow up with more observations, to pin down its path, its speed, its direction. A celestial game of connect the dots across millions of kilometers. Once confirmed, we become cosmic fortune tellers. Using Newton's laws, we calculate its orbit. This system is planetary defense. It's a global collaboration. The quiet discovery in the lonely dark is over. The clock has just started ticking for every single person on Earth, and the cosmic drama we all secretly feared has just begun. What exactly are these things we're so worried about? Asteroids are, in essence, the leftovers from the formation of our solar system. About 4.6 billion years ago, our cosmic neighborhood was a swirling disk of gas and dust around a young sun. Most of this material clumped together to form the planets. But some of the rocky and metallic debris never quite made it. These are the asteroids. They are ancient wanderers, time capsules from the birth of our world. Most of them live in a relatively stable, donut-shaped region between the orbits of Mars and Jupiter, known as the asteroid belt. Think of the asteroid belt as a cosmic rock quarry. It contains millions of objects ranging in size from small pebbles to colossal bodies hundreds of kilometers in diameter, like the dwarf planet Ceres. But their orbits aren't always perfectly stable. The immense gravity of Jupiter, our solar system's bouncer, can disturb these asteroids. A gravitational nudge can send one of these rocks careening out of the belt and onto a new path, one that might cross the orbits of other planets, including ours. These are known as near-Earth objects, or NEOs, and they are the ones we watch with great interest. When we talk about speed, it's hard to comprehend. These objects are not just drifting, they are screaming through the vacuum of space. An asteroid on a collision course with Earth could be traveling at speeds of 20 kilometers per second, or about 72,000 kilometers per hour. That's fast enough to cross the entire United States in about 4 minutes. This incredible velocity is a key part of the danger. An object's destructive energy isn't just about its size, it's about its kinetic energy, which increases with the square of its speed. Doubling the speed means quadrupling the energy of impact. So you have these ancient rocky or metallic remnants of creation, some as big as mountains, They are kicked out of their home by giant planets and sent hurtling through space at speeds that defy imagination. They are cosmic cannonballs. Our planet may seem peaceful from our perspective on the ground, but its history is written in violence. Earth bears the scars of countless past impacts. We just don't see them easily because of erosion, weather, and plate tectonics. It's like a cosmic etch-a-sketch that slowly erases its own drawings. But if you know where to look, the evidence is everywhere. Take, for example, the Barringer crater in Arizona. It's a beautifully preserved bowl in the desert, over a kilometer wide and 170 meters deep. It looks huge, but it was created by an iron asteroid only about 50 meters across. That impact happened 50,000 years ago, and it released more energy than the most powerful nuclear bomb ever detonated. It leveled everything for miles in every direction, and that was just a small one. Imagine what a larger object could do. We have found the remnants of much bigger impacts. In Canada, the Manicouagan crater is a massive ring-like lake over 70 kilometers in diameter, the visible remnant of an impact from over 200 million years ago. The Redefort Dome in South Africa is the world's largest known impact structure, originally estimated to be 300 kilometers across, left by an asteroid thought to be 10 to 15 kilometers wide. These impacts are not just historical curiosities, they are markers of planetary-scale catastrophes. Even in recent history, we've had reminders. In 1908, an object estimated to be about 60 meters across exploded in the atmosphere over a remote region of Siberia, in what is known as the Tunguska event. It flattened over 2,000 square kilometers of forest, an area larger than the city of London. If it had arrived just a few hours later, it could have detonated over a major European city. More recently, in 2013, a much smaller 20-meter asteroid exploded over Chelyabinsk, Russia. The shockwave shattered windows and injured over 1,500 people. These events prove that the threat is not hypothetical. It is real, and the question is not if another impact will happen, but when and how big it will be. If you want to understand the ultimate danger of an asteroid impact, you only need to look back 66 million years. This is when the dinosaurs, the undisputed rulers of our planet for over 150 million years, vanished. For a long time their disappearance was a mystery, but now the scientific consensus is clear. They were victims of a cosmic assassination. The culprit was an asteroid, or possibly a comet, estimated to be about 10 kilometers, or 6 miles, wide. It was a mountain of rock and ice, hurtling through space, and it had Earth in its sights. The impact site was found in the 1990s, centered on the Yucatan Peninsula in Mexico. It's called the Chicxulub crater. Today, it's buried under kilometers of sediment, but its ghostly outline, over 180 kilometers wide, is still visible in geological surveys. When that asteroid struck, it was traveling at such an immense speed that the energy released was equivalent to billions of atomic bombs. The immediate effect was apocalyptic. A fireball of vaporized rock and superheated gas expanded from the impact site, incinerating everything for thousands of kilometers. Gigantic tsunamis, hundreds of meters high, raced across the oceans. The impact ejected trillions of tons of pulverized rock, trillions of tons of dust, trillions of tons of sulfur. This material spread around the entire globe, shrouding the planet in a thick blanket of darkness. This was the impact winter. With the sun blocked out, photosynthesis stopped. Plants on land, plankton in the sea, died off en masse. The entire global food chain collapsed from the bottom up. Herbivorous dinosaurs starved first, followed quickly by the carnivores that preyed on them. This single event caused a mass extinction, wiping out about 75% of all species on Earth, including all non-avian dinosaurs. It was a planetary reset button. But here's the fascinating part: their demise was our opportunity. We are the children of that cosmic catastrophe. Let's talk about what would actually happen if our fictional asteroid 2024 XF1 were to hit us. The scale of devastation is almost impossible for the human mind to grasp. Our 10-kilometer-wide asteroid would not simply land. It would strike the Earth with such phenomenal energy that the laws of solid matter would temporarily cease to apply. The asteroid and the part of the Earth's crust it hits would behave like liquids, splashing in slow motion. The impact would create a transient crater over 100 kilometers wide in the first few seconds, vaporizing the asteroid itself and a huge chunk of our planet's surface. If it were to strike the ocean, the scenario is just as grim, if not worse. The impact would displace a colossal amount of water, creating a mega tsunami of unimaginable scale. Waves possibly kilometers high would race outwards from the impact site at the speed of a jetliner. These waves would scour coastlines across the entire ocean basin, wiping coastal cities off the map, penetrating hundreds of kilometers inland. Simultaneously, the immense heat from the impact would vaporize a vast volume of seawater, injecting it into the upper atmosphere alongside the pulverized rock, creating a global atmospheric disaster. The immediate effects at ground zero are just the opening act. The real planet killer is the atmospheric fallout. The ejecta, the debris blasted into the sky, would rain back down across the globe. As these tiny particles re-enter the atmosphere, friction would heat them to incandescence, turning the entire sky into a radiant broiler oven. The heat would be intense enough to ignite global wildfires, burning a significant portion of the planet's forests, burning a significant portion of the planet's grasslands. This would release even more soot and ash into the atmosphere, adding to the sun-blocking shroud of dust. The dust and soot would linger in the stratosphere for years, maybe even a decade. Sunlight would be reduced to a permanent twilight, causing global temperatures to plummet. Photosynthesis would fail on a planetary scale. Agriculture would collapse instantly and entirely. This is not a regional disaster, it is a global one. No matter where the asteroid hits, the consequences are felt everywhere. Okay, that all sounds pretty terrifying. And it is. But here's the good news. Unlike the dinosaurs, we have science and we have space programs. We can see it coming, and we have a plan. The first and most important part of any planetary defense strategy is detection. You can't stop what you can't see. That's why the work of those sky surveys we talked about is so critically important. Finding the asteroid is step one. The earlier we find a potential threat, the more time we have to act. The less effort is required to change its course. Time is our single greatest resource. Once we identify a hazardous asteroid and confirm its collision course, the world's space agencies would spring into action. This is where organizations like NASA's Planetary Defense Coordination Office come in. Their job is to coordinate the global response. They would double and triple check the orbital calculations. Use every available telescope to refine our knowledge of the asteroid's size, shape, rotation, composition. Is it a solid chunk of iron, or a loose rubble pile held together by gravity? Knowing what it's made of is crucial for deciding how to deal with it. The first real-world test of our ability to move an asteroid happened in 2022. It was a NASA mission called DART, Double Asteroid Redirection Test. The idea was simple, a kinetic impactor. We flew a spacecraft about the size of a vending machine. We flew it straight into a small asteroid to see if we could change its orbit. The target was Dimorphos. Dimorphos orbits a larger asteroid named Didymos, millions of miles from Earth. The mission was a spectacular success. The DART spacecraft slammed into Dimorphos at over 22,000 kilometers per h. It didn't destroy the asteroid, it wasn't meant to. It just gave it a tiny nudge. Over time, that tiny nudge adds up. The impact altered Dimorphos' orbit around Didymos, shortening its orbital period by 32 minutes. Far more than scientists had predicted. For the first time in human history, we proved we can intentionally move a celestial body. We are no longer helpless spectators. The kinetic impactor, like the DART mission, is our primary tool, especially if we have lots of warning time, years or even decades. A small nudge applied early is all you need to make an asteroid miss Earth by a safe margin. But what if we don't have decades? What if we only have a few years or even months? For a larger asteroid or a shorter timeline, we might need a more powerful push. This is where we bring in the gravity tractor, a concept that sounds like science fiction, but is based on solid physics. The idea of a gravity tractor is not to hit the asteroid but to fly a heavy, massive spacecraft alongside it for a long period of time. Everything that has mass has gravity, even a spacecraft. The tiny gravitational pull of the spacecraft, though minuscule, would be enough to slowly, gently tug the asteroid off its original course. This method is slow and controlled, which is great for avoiding the risk of breaking the asteroid into smaller, still dangerous pieces. It's a delicate cosmic dance, a gravitational tango to lead the asteroid away from danger. Then there is the most famous and most controversial option, the nuclear standoff. This doesn't mean we would fly up and detonate a nuclear bomb directly on the asteroid's surface. That would be a huge risk. If the asteroid is a rubble pile, a direct blast might just shatter it into a cloud of smaller radioactive fragments, turning one big problem into hundreds of smaller ones that could still hit Earth. Instead, the plan is to detonate a nuclear device at a close standoff distance from the asteroid. The intense X-rays and radiation from the explosion would flash vaporize a layer of the asteroid's surface. This vaporized material would shoot off the surface like a massive rocket exhaust, creating a powerful thrust that pushes the asteroid in the opposite direction. It's a much bigger and more forceful nudge than a kinetic impactor could ever provide. This is a last resort option reserved for large objects discovered with little warning time. It's a high-stakes, high-risk maneuver, but it might be the only thing standing between us and a global catastrophe. It's our emergency brake for the solar system. The thought of an asteroid apocalypse can be frightening. It taps into a deep, primal fear of forces beyond our control. For millennia, our ancestors looked up and wondered. They saw comets, they saw meteors, they felt powerless. We are not. For the first time in Earth's history, a species has the intelligence and technology to defend itself from a cosmic impact. That species is us. The dinosaurs couldn't build telescopes, they couldn't launch spacecraft. We can. Planetary defense isn't one country or one technology, it's global cooperation. Astronomers in Chile, mission controllers in Germany, rocket scientists in the United States, all working together. The threat doesn't care about borders or politics. It's a problem for every human. It can be a great unifier. We are all crew on the same fragile spaceship Earth. Our journey into space gave us perspective. From the moon, we don't see borders. From the orbit of Mars, we don't see borders. We see a single, beautiful, interconnected world. A tiny oasis in vast darkness. This is the overview effect. It reminds us what's at stake. Our squabbles seem small against the cosmos. Protecting our world transcends our differences. The universe holds dangers and wonder. The same science that finds threats helps us understand the origins of the universe, helps us explore other worlds, helps us dream of a future among the stars. We are curious and resilient. We solve problems. We work together when it matters. The sky is not falling. We are learning to hold it up. If we invest in science, look to the stars with curiosity, not fear, and work together as one people on one planet, then our future is not doom but infinite hope.